Good morning to all. We will continue with our discussion in magnetostatics. We started looking at a current carrying loop placed in a magnetic field, and I showed last time that if you have a current carrying coil placed in a uniform magnetic field, then the magnetic field applies a torque on the coil and tries to align the coil towards the direction of the magnetic field. And so, this torque is essentially given by, so let me recall. So, if you have a coil, if you consider a rectangular coil and if you place it in a magnetic field in some arbitrary direction carrying a current, then the torque is equal to m cross b, where m is the magnetic dipole moment of the coil and b is the magnetic field. So, there is an external magnetic field which is applied on the coil, and the coil then has a torque on it because of the magnetic field, and the torque tends to rotate the coil towards the magnetic field. And we started looking at one application of this particular phenomenon, and that is in a moving coil galvanometer. So, in electrical circuits we need to have instruments which measure the current passing through the circuit or measure the potential difference across different circuit elements. The instrument that measures the current passing through the circuit is called an ammeter, and the instrument that is used to measure the voltage across potential difference across circuit elements is called a voltmeter. So, we will now consider a galvanometer first to show you how I can make an instrument which will help me to measure currents and potential differences. So, the galvanometer consists of let me draw the figure here. So, I have a permanent magnet shaped in this form. This is one piece here, another piece here, and there is in the center there is a soft iron cylinder, and the magnetic field lines of this magnet are coming like this, or radial, they are pointing towards the center of this. So, this particular portion acts like the north pole, here is the south pole. So, magnetic field lines going from this side to this side through the soft iron core. Now, I have a coil placed on in this. So, there is a coil running like this which has a number of turns which is carrying the current, and the coil is attached to a spring, and there is a pointer. So, there are divisions here. So, now let me look at the operation of this. So, please note that there is a magnetic field perpendicular to the direction of the coil. The coil is vertical like this. So, the coil is coming up from here and going back. So, there is a coil is like this around the soft iron core, and this coil is current carrying coil is free to rotate about this axis here, and it is connected to a spring. So, when a current passes through this coil, the magnetic field applies a torque on this coil, which then tends to rotate the coil in this direction. When the coil rotates, the spring actually gives it a restoring force, which then the coil then comes to an equilibrium position where the torque due to the magnetic field and torque due to the spring are equal and opposite to each other. So, when you pass a current through the coil, the needle here will rotate because the current passing through the coil is acted upon by a torque of the magnetic field, external magnetic field that is applied from the magnet, permanent magnets, and that torque then makes the coil rotate, and the spring actually gives it a restoring force, which then the coil rotates up to a certain angle when the two become equal and opposite, and the coil the pointer stops at that point, and that gives me an indication of the current that is passing through the coil. So, we because you can see here that the current is always perpendicular to the direction of magnetic field, the magnetic field is radial pointing toward the center here. So, the current carrying conductor is always perpendicular to the coil, and so we can write the torque due to the current is equal to m cross B, which is actually m times B, because the dipole moment is always perpendicular to the magnetic field here, and if there are n turns and the current is and the area of the loop is A, so m is actually n times I times A into B. So, A is the area of the loop, I is the current passing through this. So, for one loop the dipole moment is I times A, and if I have n such loops, closely bound n loops, the total dipole moment is NIA, and the tau due to current is NIAB. Now, the spring has its own spring constant. So, I can write the torque due to the spring, which is equal to some constant times the angle of rotation. So, K is the spring constant, and phi is the angle of rotation. So, when these two become equal and opposite, the deflection will stop. So, I get an equation at equilibrium K times phi is equal to N I A into B, which gives me phi is equal to N times A B times by K into I. So, you can see that the deflection of the needle here, the deflection of the needle is proportional to the current that is passing through the coil. So, as you change the coil current, as you change the current in the coil, the deflection will change, and as the current increases, the deflection continues to increase. And so, I can actually measure, I can actually relate the angle of deflection of this coil to the current that is passing through the coil, and that is the galvanometer, and it is a very useful instrument that it can be used to measure current passing through a circuit, etc. So, let me look at the two examples of how to use a galvanometer as an ammeter. An ammeter is an instrument that is used to measure current through a circuit. So, if you have a circuit, for example, if you have a wire here, circuit, part of a circuit which is carrying current I must be able to connect an instrument here, I must be able to connect an instrument here and be able to measure this current I. So, that is ammeter here. Now, please remember that the ammeter, connecting the ammeter should not change the conditions of the circuit. If the ammeter, for example, has a large resistance, then it will change the total resistance of the circuit, which will then change the current I that is passing through the circuit. My objective is to measure the current I passing through the circuit, and so I must ensure that the ammeter which I connect must have very low resistance. In fact, in principle I should have an ammeter with 0 resistance. So, here 0 would imply essentially a very, very small resistance. So, how do I use this? So, here is my circuit carrying current I. So, I connect this is the galvanometer, and I connect a resistance in parallel with the galvanometer and connect here. So, this is, let me call it RS, and let me call RG as the galvanometer resistance. RG is the resistance of the galvanometer, RS is the resistance of the resistor which is connected in parallel to the galvanometer. So, you know that the total resistance, the net resistance of this is 1 by R is equal to 1 by Rg plus 1 by Rs, which is equal to Rs plus Rg by Rs Rg. So, that gives me the equivalent resistance as R is equal to Rs Rg by Rs plus Rg. This is the resistance of this part of the circuit. This is my ammeter now. This will I want to make this as the ammeter. So, the resistance of this which I have added to the circuit is given by this. Now, I want this resistance to be very, very small. So, I take a resistance Rs which is much less than Rg. So, if Rs is much less than Rg, then R becomes approximately equal to Rs into Rg by Rg, which is equal to Rs. So, if you connect a parallel resistance here with the galvanometer, which is a very, very small resistance, then the net resistance of this is very small and almost equal to Rs. If Rs is much smaller than Rg, then the total resistance of the circuit is simply equal to Rs. So, to convert a galvanometer into an ammeter current measuring device, I must connect a resistance called the shunt resistance here, which is in parallel with the galvanometer, and the total resistance of this is almost equal to the resistance Rs. Now, let me consider an example. Okay. So, I want to consider an example in which I have a galvanometer with coil resistance of 20 ohms, that is Rg is equal to 20 ohms. Okay, that is given to me, and I also know that full deflection of the galvanometer takes place for I is equal to 1 milliampere. So, what it implies is if 1 milliampere passes through the galvanometer, the needle goes from 0 position to the maximum position. So, the maximum current I can pass through the galvanometer is 1 milliampere. Now, I want to convert this galvanometer into an ammeter. To convert to an ammeter, capable of measuring up to 100 milliamperes. So, what I want to do is to have this galvanometer converted to an ammeter, in which if I have 100 milliamperes in my circuit, I will get full deflection. So, it can measure, this ammeter will be able to measure currents from 0 to 100 milliamperes. Now, so I need to calculate what is the Rs I must add to this galvanometer to be able to measure this. So, let me draw this circuit here again. So, this is my Rs, this is Rg, this is I coming from here, this is Rs, this is Rg, I is going back here. So, this is actually, let me call this Ig and let me call this Is. So, I have total current is equal to Is plus Ig. The total current splits into an Ig goes into the galvanometer and I is going through the shunt, and because between these 2 points the potential difference is some potential difference that is the same whether I look at this current or this current. So, I also have an equation Ig into Rg, which is the potential difference between these two this point is equal to Is into Rs, which is the potential difference across this resistance Rs. So, I can use all this to simplify. So, I is equal to Ig into 1 plus Is by Ig, which is equal to Ig into 1 plus, now Is by Ig from here is Rg by Rs. So, this gives me Ig into Rs plus Rg by Rs. So, now I can simplify this equation further and I get an expression for Rs from here. So, Rs comes out to be Ig Rg by I minus Ig. This equation, you can simplify this equation to calculate Rs. You take Rs on the left hand side, and so you get Rs into I minus Ig is equal to Ig Rg, and I get this equation. So, now I am given in my problem Rg is equal to 20 ohms. The maximum current in the galvanometer is equal to 1 milliampere, and I must go up to I is equal to 100 milliamperes. That means, when I have 100 milliamperes in my circuit, when I have 100 milliamperes in my circuit here, this current must be 1 milliampere. So, that I will be able to measure all currents up to 100 milliamperes. So, substituting this gives me Rs is equal to 1 milliampere 10 to the minus 3 into Rg, which is 20 ohms, divided by I is 100 milliamperes minus 1 into 10 to the minus 3, which is equal to 20 by 99, which is approximately equal to 0.202 ohm. So, what we have got is, if I had a galvanometer with a resistance of 20 ohms, and if it is capable of measuring up to 1 milliampere, which means that at 1 milliampere I get full deflection, then to convert this galvanometer into an ammeter, which is capable of measuring up to 100 milliamperes, I must connect a resistance in parallel with the galvanometer whose value is about 0.202 ohms. So, if I connect 0.202 ohms here, when 100 milliamperes comes from here, I have 1 milliampere going through this and remaining 99 milliamperes going through this. So, as I change my current here, the fraction here changes and I get essentially the deflection on the galvanometer, which tells me how much of current is passing through the circuit. So, that is an example of converting a galvanometer into an ammeter. Now, let me look at another example of galvanometer to voltmeter. So, I could have a circuit in which I have some circuit element here, and I want to measure the potential difference across this 2 points. So, the voltmeter is a device which I will connect across this and measure the potential difference across these 2 points. Again, I must ensure that connecting the voltmeter to the circuit does not change the current passing through the circuit, which means because this voltmeter is in parallel with the circuit here, the voltmeter must have very high resistance, so that adding this does not cause much change in the circuit, and the current that was passing before I connected the voltmeter continues to pass in the circuit. So, to increase the resistance, what I need to do is to connect another resistance in series with the galvanometer. So, let me draw the figure again here. So, that is my circuit element, and I connect a resistance and the galvanometer here. So, that is the galvanometer, this is R, let me call it Rp, this is Rg. So, the total resistance of this part now is R is equal to Rp plus Rg, which is approximately Rp for Rp much greater than Rg. So, I must, if I connect a very high resistance in series with the galvanometer, the total resistance of this Rp and Rg combination is approximately equal to Rg, and that is very large, and when that is very large, connecting this to the circuit should not much alter the current passing through the circuit. So, now let me take the same example which I had done before, a galvanometer with a resistance of 20 ohms and the maximum full scale current 1 milliampere. That means, if 1 milliampere passes through the galvanometer, the deflection is complete, and I want to convert this to a voltmeter to measure up to 10 volts. So, I want to be able to convert a galvanometer into a voltmeter, which will be able to measure potential differences of up to 10 volts. So, here is my circuit here. So, I can write now. So, let me draw the circuit again here. So, this is the current element, Rp, Rg. Now, the current, so let me call this as the I galvanometer and I circuit. So, this is the current which is coming is I. So, I is equal to I galvanometer plus IC, and the potential difference across this V is equal to Ig into Rp plus Rg okay. So, let me simplify this. For we want Ig to be 1 milliampere when V is equal to 10 volts. When V is equal to 10 volts, I want Ig to be 1 milliampere. So, I can simplify this equation. So, I will get Rp is equal to V minus Ig Rg by Ig, which is equal to 10 minus Ig is 1 milliampere into Rg is 20 ohms divided by Ig is 10 to the minus 3, which is approximately 9,980 ohms. So, you can see here the resistance of this is now very large compared to the galvanometer resistance, which is 20 ohms. So, if I connect about 9,980 ohms in series with the galvanometer, I can convert the galvanometer into voltmeter that is capable of measuring up to 10 volts. That means, when the potential difference across these 2 points becomes 10 volts, I get full scale deflection, because at that point the current passing through the galvanometer is 1 milliampere, which leads to full deflection of my galvanometer pointer. So, a galvanometer is a device which has a coil placed in a permanent magnet in the magnetic field produced by permanent magnet, and as soon as current flows through the coil, the magnetic field applies a torque on the coil, which makes the coil rotate, and the coil is connected to spring, which actually does not allow the coil to rotate too much, and it sort of gives a restoring force, and there is an equilibrium point at which the torque due to the magnetic field is exactly equal to the torque due to the spring, and the needle stops at that point. So, I can measure very sensitive currents through this, and I have 2 examples in which I have seen how to convert a galvanometer into an ammeter, which will measure currents passing through the circuit, or a voltmeter to measure the potential differences across different points in an electronic circuit. So, these 2 examples tell us how torques in the presence of magnetic fields can be used to measure currents and potential differences across in a circuit. Now, I want to come back and look at the magnetic dipoles itself and look at some other properties of magnetic dipoles. So, let me recall that we had calculated the magnetic field due to a circular loop of current. Remember, we had done this example. Point here, there is a current I flowing through this. This is a coil of this radius r, we had calculated the magnetic field along the axis. B is equal to mu naught I r square by 2 times z square plus r square raised to the power 3 by 2 k cap. This is along the axis, around this axis, z axis, that is the magnetic field. For z much greater than r, B is approximately equal to mu naught I r square by 2 z cube, which I wrote as mu naught m k cap by 2 pi z cube, where m is the magnetic dipole moment, which is I into pi r square, and magnitude is this, and the direction is using right-handed screw rule. So, that is the magnetic dipole moment is like this. The current is passing like this. So, the dipole moment is oriented in this direction, and as you can see here along the axis, the magnetic field is parallel to the dipole moment, and it decreases as 1 by distance cube from the center of the coil and the dipole. So, although I have derived this for a circular loop, this equation is valid in general for a planar loop with a magnetic dipole moment m, which is actually the current passing through the coil multiplied by the area of the coil, and the direction of the dipole moment is obtained by using right-handed rule. So, if you have a coil which is carrying current like this, then the magnetic dipole moment is pointing upwards. If you have a current going like this, then the magnetic dipole moment is pointing inwards. So, that gives me the magnetic field along the axis of the dipole. Now, I wish to calculate magnetic field in a plane of the dipole. Now, so I want to know a calculation for magnetic field in the plane of the current loop. So, let me draw the current loop here. So, this is my loop now. So, let me call this x axis, this is y axis, and z axis is pointing towards me here, and let me assume a current I is flowing through this. So, this calculation, in the earlier calculation we had looked at this was the current carrying loop, and I had looked at the magnetic field along the axis of the dipole. Now, I want to calculate, if I have a loop like this, horizontal carrying current like this, I want to calculate the magnetic field in this plane and at a distance x from here. So, I will use Biot-Savart law and simplify, and I want to calculate for, if this distance is x here and this radius is r, I want to calculate for x much greater than r. Just like before, I want to calculate the magnetic field at distances much larger than the radius of the loop, and I want to calculate at this point. So, I will use Biot-Savart law. So, recall what I need to do is I need to consider a current element here dl, then this is my r vector, and I will have to calculate. So, I calculate the magnetic field here by integrating over the entire circuit. So, I take current elements at different points in the circuit and calculate. So, first let me write down. So, let me assume that this position is theta, this current element subtends an angle d theta. So, what is r vector? R vector is the vector joining this point to this point. So, this point has coordinates x 0, and that point has coordinates, this point has the other point has coordinates which are so you have r cos theta along x and r sin theta along y. So, r vector will be x minus r cos theta I cap minus r sin theta j cap. So, this is my r vector, and as theta changes, as I move my dl current element along the loop, theta changes and this r vector changes. I also need an expression for dl because Biot-Savart law has dl cross r. So, I need to calculate dl. So, dl vector, now this is let me draw a figure here x y. So, dl vector is like this and this angle is theta. X y. So, you can see the x component is negative and minus dl sin theta and the y component is positive. So, plus dl cos theta j cap. This line is perpendicular to this line is perpendicular to this line and so this angle is theta. So, dl minus dl sin theta I, and if this radius is r and this angle is d theta, dl is nothing but dl is equal to r d theta. So, this is equal to minus r d theta sin theta I cap plus r d theta cos theta j cap. So, that is dl vector, r vector, dl vector. So, let me calculate dl cross r. Which is equal to, so dl vector is minus r sin theta d theta I cap plus r cos theta d theta j cap cross r vector is x minus r cos theta I cap minus r sin theta j cap. So, I cap cross I cap is 0 and I get r square sin square theta d theta, I cap cross j cap is k cap, r cap. So, this j cap cross j cap is 0. So, I have the first one plus r cos theta into x minus r cos theta d theta, j cap cross I cap is minus k cap. So, there is a minus sign here with a k cap. So, this is equal to, now there is r square sin square theta d theta k cap. When I open this up, so I get r square sin square theta d theta k cap minus r x cos theta d theta k cap plus r square cos square theta d theta k cap. So, this plus this gives me simply r square. So, r square d theta k cap minus r x cos theta d theta k cap. So, dl cross r is as only one component which is k cap component. So, I can use this. So, this is dl cross r and I need also r cube which is actually equal to, so r vector is here. So, r cube is nothing but x minus r cos theta whole square plus r square sin square theta whole raised per 3 by 2. Okay. So, that is r cube. So, let me substitute both of them into Biot-Savart law to get the magnetic field. So, B is equal to, remember Biot-Savart law, mu 0 I by 4 pi integral dl cross r by r cube, which is equal to mu naught I by 4 pi now dl cross r, I can take out one r common. So, I get r integral 0 to 2 pi r minus x cos theta d theta divided by x minus r cos theta whole square plus r square sin square theta raised to power 3 by 2 and there is a k cap. So, what I have done is I have replaced dl cross r by, so if I take out r d theta k cap common. So, I get r minus r minus x cos theta d theta k cap, and the denominator we have this expression. Now, that is I have not made any approximation as yet. This is the magnetic field at a distance x from the center of the coil in the plane of the coil. Now, I want to make an approximation for x much greater than r. So, I want to expand the denominator here. So, let me write this. So, x minus r cos theta whole square plus r square sin square theta, which is equal to x square plus r square cos square theta plus 2 x r cos theta plus r square sin square theta, which is equal to x square plus r square plus 2 x r cos theta minus 2 x r minus 2. So, this is equal to x square into 1 minus 2 r by x cos theta plus r square by x square. So, now please remember, when I make approximations, I must keep track of the terms up to a certain order, and I must ensure that I do not neglect terms of same order from some other part of the expression. So, that is why I am very carefully expanding and calculating this component here. So, I need to make sure that this total integrand, the approximate value of this for x much greater than r. So, what happened to the denominator now? So, this denominator has the same quantity raised to 3 by 2. So, let me calculate x minus r cos theta whole square plus r square sin square theta raised to 3 by 2, which is equal to x cube into 1 minus 2 r by x cos theta plus r square by x square raised to the power 3 by 2. So, 1 divided by this expression x minus r cos theta whole square plus r square sin square theta raised to the power 3 by 2, which is equal to 1 by x cube into 1 minus 2 r by x cos theta plus r square by x square raised to the power minus 3 by 2. And I can make a binomial expansion here. So, this is approximately 1 by x cube into 1 plus 3 r by x cos theta, where I have neglected higher order terms of the order of 1 by x square. So, remember this is r square by x square, the square of this is r square by x square, etc. So, I have retained terms up to order r by x in this expression. So, now let me calculate. So, this I have got an approximate expression for the denominator, I have the numerator sitting there. So, let me substitute into this equation. So, B is equal to mu naught I r by 4 pi integral 0 to 2 pi r minus x cos theta 1 by x cube into 1 plus 3 r by x cos theta d theta k cap. So, let me expand this. So, mu 0 I r by 4 pi 0 to 2 pi, I get r into 1 is r, and then I get second term is minus 3 r cos square theta, then I have minus x cos theta, then I have minus x cos theta plus 3 r square by x cos theta d theta k cap, and there is an x cube, this denominator x cube. Now, you see here that integral 0 to 2 pi cos theta is 0, this will give me 0. I need to look at this equation, this part now. So, this is mu 0 I r by 4 pi x cube So, r comes out. So, it is 0 to 2 pi, 0 to 2 pi 1 minus 3. Now, cos square theta, I know expression. So, cos 2 theta is 2 cos square theta minus 1. So, I can write this as 3. So, cos, let me write here, cos 2 theta is 2 cos square theta minus 1. So, this cos square theta is 1 plus cos 2 theta by 2 into r, sorry, r is taken out, into d theta k cap. Now, again if I open this up, I get 3 by 2 and 3 cos 2 theta by 2, cos 2 theta integral will become 0, and I will get finally an expression for b is equal to mu 0 I r square by 4 pi x cube 0 to 2 pi. So, 1 minus 3 by 2 is minus half d theta. So, this is simple integral. So, it just gives me minus half into 2 pi. So, I get b is equal to minus mu 0 I r square by 4 pi x cube into pi into k cap. So, I get an equation for this, and recall that the magnetic dipole moment is defined as I times pi r square to k cap. So, B becomes equal to minus mu naught m by 4 pi x for x. So, if this is the current loop carrying current at this point, so you look at this thing now. This current is flowing like this, that is the current. So, m is pointing towards me, and so this magnetic field is pointing towards minus m cap direction. So, remember this current is going like this and here. So, this current produces a downward magnetic field, this current produces an upward magnetic field, and the distances being unequal, the net magnetic field is downward opposite to the direction of the magnetic dipole moment. So, we have got expressions for the dipole moment of a circular coil. So, let me recall here. So, if I have a magnetic dipole moment m, so B along axis for z much greater than r is equal to mu naught m by 2 pi z cube, and B in the plane minus mu naught m by 4 pi. So, these are along two particular orientations. You can actually calculate in general, and we will not do it in the course here, but we have seen that we can use Biot-Savart law to get an approximate expression for the magnetic field produced by a magnetic dipole in the plane. And please remember, just like we had in the case of electric dipoles, we can have point magnetic dipoles where the area of the loop is very small, there is a current flowing through the circuit, and it almost acts like a point dipole. For distances very large compared to the size of the dipole acts like a point dipole, and these are the magnetic fields produced by these dipoles along the axis of the dipole and in the plane containing the dipole. So, we have been able to obtain expressions for the magnetic field produced by the dipoles in the axis, along the axis of the dipole and in the plane of the dipole. Now, remember, in the case of electric dipoles, we had calculated the potential energy of the dipole. So, if you place an electric dipole in an electric field, the electric field applies the torque on the dipole and aligns the dipole with respect to the electric field. Similarly, we have seen here that when you have a magnetic dipole, the magnetic field tries to align the magnetic dipole along the magnetic field direction. So, I want to calculate the potential energy of a magnetic dipole placed in the magnetic field. So, when a magnetic dipole changes its orientation because of a torque, then it changes its potential energy. So, I want to calculate this potential energy change. So, let me take a particular axis. So, x, y, z. Let me assume a magnetic field like this. So, B field is like this, and let me assume a dipole placed like this. Make an angle theta with the magnetic field direction. So, the coil, current carrying coil is like this to give a magnetic dipole moment. So, there is a magnetic dipole which is pointing at an angle theta with the magnetic field. So, what is the expression for the magnetic field? B is equal to B into j cap. It is along the y direction. The dipole moment, it has a y component and a z component. So, this is m cos theta j cap plus m sin theta k cap. This magnetic dipole has a component along the y direction. So, I am assuming that the magnetic dipole is in the yz plane and the direction of the magnetic field is along y. So, torque due to magnetic field is equal to m cross b, which is equal to m cos theta j cap plus m sin theta k cap cross b j cap. J cap cross j cap is 0, k cap cross j cap is minus I cap. So, I get minus m b sin theta I cap. So, the torque, magnetic torque direction is along the minus x direction because it is trying to rotate the m vector along the direction of the magnetic field. So, the torque is in this direction, the reverse direction. So, it is acting like this, and that is the minus I cap direction. Now, if I have to change the orientation of the dipole, if I have to rotate the orientation of the dipole in some other orientation, I need to do work because the magnetic torque is trying to push it towards the direction, and if I need to rotate the magnetic dipole along some other direction, I need to do work on the magnetic dipole to change its orientation, and that work which I do gets stored in the form of potential energy in the dipole, and that is what I want to calculate. So, the external torque which I need to apply tau external will be minus of this is opposite direction. So, I must have m b sin theta I cap. The magnetic field is trying to apply a torque to orient the dipole along the B field direction. If I want to move it along some other direction, depending on the direction of motion, I will have to do work, or the field does work. So, if I want to increase theta, I need to do work on the dipole, and that work which I do gets stored in the form of potential energy of the dipole, which I want to calculate. So, the torque which I have to apply is negative of this, which is plus m b sin theta I cap. So, change in potential energy in rotating the dipole from theta 1 to theta 2 is u is equal to integral theta 1 to theta 2, the tau external multiplied by d theta, which is equal to m b theta 1 to theta 2 sin theta d theta, which is equal to minus m b cos theta 2 minus cos theta 1. That is the work which I need to do in rotating the dipole from an angle theta 1 to another angle theta 2. So, now remember in the electrostatic case we had defined the 0 potential energy at some orientation. Here also we will define the 0 potential energy to be at theta is equal to pi by 2. So, for an angle theta, orientation, the potential energy u is equal to minus mb. So, what I will do is replace theta 1 by pi by 2, cos pi by 2 is 0, theta 2 by theta. So, I get minus mb cos theta, which is equal to minus m dot b. So, that is the potential energy of the dipole minus m dot b, and so minimum potential energy for which is equal to minus mb for theta is equal to 0, and maximum for is equal to plus mb for theta is equal to pi. So, let me draw a figure here to show you. So, if I have a magnetic field pointing up, if you have the if you have a dipole like this, current flowing like this, then minimum, and if I have current flowing in the opposite direction with m like this, then maximum. So, if the magnetic field is pointing upwards and if my dipole is pointing downwards, I have maximum potential energy, and if I rotate it to the other direction, I have minimum potential energy when the magnetic dipoles are aligned with respect to the magnetic field, and this gives me an energy, potential energy of the dipole, which is minus m dot b. So, whenever you place a dipole in a magnetic field, the magnetic field will apply a torque on the dipole, and that torque will try to align the dipole, and if you want to change its alignment, you need to do external work. Now, we will come across these dipoles in when we study magnetism of matter, because matter will consist of essentially a large number of dipoles. These are currents which are passing within the material, and we will come across the torques and the energy of these dipoles a little later. Now, although I have obtained this equation for a planar loop, this equation for a planar circular loop, these equations are valid for any planar loop of any arbitrary shape, where m will represent the magnetic dipole moment and b is the external magnetic field. Please remember, this is the external magnetic field and this is the dipole moment of the dipole that you are placing in the external field. So, these are important considerations for magnetic dipoles, and we will use this for looking at dipoles in matter. Now, I want to look at one example here. So, let me assume I have a loop carrying current like this, placed in a magnetic field. So, let me call this x and this is y. So, this is z and y axis is like this, and I have a magnetic field which is pointing like this, and because the current is going like this, m vector is here. So, radius r is equal to 5 centimeter current I is equal to 5 amperes, and let me assume a magnetic field of 0.1 Tesla. So, what I want to do is I want to calculate what is the magnetic moment of this. So, I leave this problem to you, calculate the magnetic moment. We will discuss this in the next class again, calculate the magnetic moment of the loop, then calculate the torque on the coil and calculate the change in potential energy when it goes from this position So, we will discuss this in the next class, but in the meantime I would urge you to think about this. Using these numbers, calculate the magnetic moment of the loop, the torque on the magnetic on the coil, and also the change in potential energy when the dipole goes from this position to the minimum position. Thank you.